two equations that we have that describes the mathematics of lenses. Our lens equation, 1 over f is equal to 1 over do plus 1 over di. And then we have our magnification equation, m is equal to hi over ho equals negative di over do. Remember, units can be anything we want here. Usually we use centimeters as opposed to meters here, just because it's convenient though. If we have meters, that's fine too, or even kilometers or feet or inches. It doesn't really matter as long as you're consistent. What does do stand for? Yeah, that's the object distance. That's the distance from the lens to the object, to the whatever it is that we're trying to project through this lens. Di is the image distance. This is the distance from the lens to wherever the image is formed. Sometimes it's formed on a screen, it's a real image. Sometimes it's not formed on a screen. You have to look through the lens to see it. That's a virtual image. Wherever it is, real or virtual, Di is the distance between the image and the lens. F is the focal length. Okay, that focal point that we had all the rays that were parallel to the principal axis going through, yeah, that's the focal point. The distance from that focal point to the lens is your focal length. Hi is your image height, how tall the image is. Again, usually in centimeters. It can be whatever you want though. Ho is the height of the object. Okay, sometimes the image is taller than the object, sometimes the image is shorter than the object. And m is the magnification. That's the ratio of the image height to the object height. In other words, how tall the image is compared to the object. If we have a number that's greater than 1, the image is bigger. If we have a number that's less than 1, the image is smaller. Now let's talk about some signs. We gave you a table the other day. And I'm just going to summarize that table for you right now, just to refresh your memory on those signs. F, do, and di kind of go together here. If we have f, do, and di, they're positive or negative based on whether they're real or virtual. In other words, if we have a real focal point, then f is positive. If we have a real object, then do is positive. If we have a real image, then di is positive. Now, when do you have a real focal point? You have a real focal point when you have a converging lens. When rays of light actually really converge through the focal point, then it's a real focal point. If a virtual focal point or a negative focal length, if you have a diverging lens. So those rays of light diverge away from the focal point. Right? So it's like this. This kind of lens causes the rays to come together at that focal point. This kind of lens causes the rays of light to diverge or go away from the focal point. This would be a positive focal length. This would be a negative focal length. Does that make sense? Do will always be positive for us. In Physics 30, you're never going to see a situation where the object is virtual. So do will always be positive. In di, well, you know that the image is virtual most times. If you think back to your ray diagrams that we drew the other day, and the patterns of the ray diagrams, we started off with converging lenses. And in those converging lenses we had, firstly, we had smaller, real, inverted. We had same size, real, inverted. We had bigger, real, inverted. Do you remember what the next one was? Boom. No image. And then we had bigger, upright, and virtual. And then for the other kind of lens, for the diverging lens, we had smaller, upright, and virtual for all of them. So 6 times out of 10, we have a virtual image or a negative di. 3 times out of 10, we have a positive di because we have a real image. And 1 time out of 10, we have no image whatsoever. So if you got a guess on that, guess a negative di because 6 times out of 10, you're right there. Does that make sense? Now, what about M, Hi, and Ho? M, Hi, and Ho are not based on whether they're real or virtual, but rather M, Hi, and Ho are based on whether they're upright or inverted. We get an upright image whenever it's virtual. So in other words, 6 times out of 10, we have an upright image, and Hi and therefore M would be a positive value. 3 times out of 10, we get a virtual image, a real image, which is inverted. The real images, if you think back to your ray diagrams, are always inverted. 3 times out of 10 an inverted image, so DI would be negative, and then 1 time out of 10, there is no image. So if you can remember these, right, FDO and DI go with real or virtual, MHI and HO go with upright or inverted, you should be good to go. Let's take a look at our 4 questions for homework that we had. Worksheet number 18 on curved lenses here. We'll go through all 4 of these questions here, starting with question number 1. It says a 12 centimeter tall object. What variable are we given here? A 12 centimeter tall object. That's HO, right? We're going to say HO is 12.0 centimeters. It's placed 15 centimeters in front of a converging lens. Okay, what's that 15 centimeters thing? What is it? DO. By the way, HO we made positive because normally we can assume the object is right side up unless it says otherwise. The object will be right side up. DO will always be positive because we always have a real object. It's a converging lens. This is important, actually. You probably should have identified this first. A converging lens has a positive focal point. You got that? If it was a diverging lens, it would have a negative focal point. You should, every time you see one of these questions, circle that, highlight it, whatever, draw attention to that. If it's diverging, you need to make that focal point negative. But this isn't. This is converging, so we're going to say the focal point is positive 10.0 centimeters. We want to find DI, we want to find HI, we want to find M, and then we want to find the attributes. And we're just going to find the attributes after we're done doing our calculations here. I'm going to start off with the lens equation. 1 over F is equal to 1 over DO plus 1 over DI. 1 over 10 is equal to 1 over 15 plus 1 over DI. You can see here if I put a negative in there by mistake, or if I forgot to put a negative in there that should be in there, you can see here that this isn't going to work out, right? The fractions are not going to work out. You guys remember what I did with this the other day, the little trick with this? You can add fractions by finding a common denominator, right? You can do that. Okay, be my guest. I'm not going to do that, because in the end, there's a little trick on our calculator that can help us with that. I'm going to say 1 over 10, x to 10, which is 10x to the minus 1. Now I'm going to take the 1 over 15 over by subtracting. So 1 over 10 minus 1 over 15. I'm going to press enter. Is that my answer? No, that's not my answer. That's 1 over DI, right? I want to find DI. I'm going to flip that over. We get a value of 30. So DI is equal to 30 centimeters. There's DI. Right away, we get a positive DI. Let's go back to our little sign conventions here. A positive DI means what? Yeah, it means the image is real. A positive DI doesn't say anything about the object or the focal point. A positive DI means real, but specifically, it's DI, so it means the image is real. So right away, we know one of the attributes here, right? We know that it's a real image. Now let's find something else. Let's find M now. Let's find M by saying M is equal to negative DI over DO. It's equal to HI over HO, but it's also equal to negative DI over DO. So let's say negative 30 divided by, so what's the value of DO? 15 centimeters, positive 15 centimeters because it's a real object, as it always is. Negative 30 divided by 15 gives me negative 2.0. No units with that, because the units cancel out, just negative 2.0. So we know now, if our magnification is 2.0, we know now that the image is larger. If the magnification is bigger than 1, we have a bigger image. If the magnification is less than 1, we have a smaller image. So we got 2 of our characteristics. It's real and it's larger. We also know that it's inverted, because if we think back to our sign conventions here, a negative HI refers to inverted. FDO and DI go with real or virtual. MHI and HO go with upright or inverted. Now we want to find we got all our characteristics now. Let's find our image height now. For that, we're just going to say M is equal to HI over HO. HI is equal to M times HO. We already have the value of M. It's negative 2. Just found it. HO is 12. Multiply those together, we're going to get negative 24 centimeters. Negative there tells me that it's inverted as well, although we already determined that from our negative magnification. Let's do example number 2 now. 12 centimeter tall object, that's going to be HO, the height of our object is 12 centimeters. It's placed 15 centimeters in front of a diverging lens. Our object distance is 15 centimeters. DO will always be positive. HO will almost always be positive. Be careful with this. We have a diverging lens. A diverging lens means that we have a negative focal point. So we're going to say that F is equal to not 10, but negative 10. Converging lens is a positive focal point. Diverging lens is a negative focal point. We want to find DI. We want to find HI. We want to find M. And we want to find the attributes. Pretty much the same as you did in the last question, except that we have a negative focal point here. 1 over F is equal to 1 over DO plus 1 over DI. 1 over negative 10 is equal to 1 over 15 plus 1 over DI. Do a little calculator trick on this. We're going to say 1 over negative 10, which is negative 10x to the minus 1. Let's subtract 1 over 15. That gives us 1 over DI. Let's flip that over. Gives us a value of negative 6. We have a negative 6 centimeter DI. The negative there means that it is a virtual image. And if we go back to our conventions, F, DO, and DI, positive, negative go with real or virtual. So a negative DI means it's a virtual image. Spelled it wrong, but it's still virtual. Then we use our magnification equation. M is equal to negative DI over DO. Negative 6, because DI is negative, take the negative of that, divide it by 15. That gives us a magnification of positive 0.40. A magnification that's less than 1 means that the image is smaller, and a magnification that's positive means that it is upright. Finally, we're solving for DI here. Let's say we're solving for HI. M is equal to HI over HO. HI is M times HO. So we're going to say 0.4 times my object height. How tall the object is 12 centimeters. 0.4 times 12 is 4.8 centimeters. The positive again tells me that it's upright. I didn't need that because my magnification is positive. It already told me that it was upright. You can see here though that the image height is 4.8, the object height is is 12. We predicted based on the magnification that the image would be smaller, and sure enough it is. It's 4.8 compared to the object, our original object, which is 12 centimeters. 3. The image created from a 10 centimeter tall upright object. That will be HO. HO is upright, it's positive. It's placed 5 centimeters from a lens. That's going to be DO. And DO is always positive 5 for us, or always positive at least. The image created is 4 centimeters tall. That means our image height is 4.00 centimeters, and it tells me in the question that it's upright. We're going to determine the magnification, the image distance, the focal length of the lens, the attributes, and the type of lens that we have. So what do we want to start off with? Well, we really have like 3 equations. Let's go with 1 over F is equal to 1 over DO plus 1 over DI. F we don't know. DO we have. DO we don't have DI or F. So we can't do that. Let's try one of our other equations. M is equal to, let's go HI over HO. HI is 4. HO is 10. That gives me 0.400. If the magnification is 0.4, is the image bigger or smaller than the object? Trent? Correct. Because the image, the ratio of the image height to the object height is 0.4, it's less than 1, the image is smaller than the object. So when you look into that lens, or when you project it onto the screen, it appears smaller than it really is. Because it's a positive magnification, the image is going to be right side up or upside down. Alex? Oh, CJ? Right side up, good. Excellent. Now let's find something else here. We could probably find DI now. Let's say M is equal to negative DI over DO, and solve for DI. It becomes negative M times DO. Negative 0.400. We're not saying the magnification is negative 0.4 there. We're just saying negative of positive 4 times my object distance, which is 5. That gives me, I believe it's 2. Is it? Yes. Negative 2.00 centimeters. Negative 2 centimeters is my image distance. If we go back to our conventions, back here we are. A negative DI means that we have what type of image? A negative DI means we have a virtual image. F, DO, and DI go with real and virtual. Positive values mean real, negative values mean virtual. So we're going to say right now that this image is virtual. And finally, we want to find the focal length as well and the type of lens that we have. So let's say 1 over F is equal to 1 over DO, which is 5, plus 1 over DI, which is negative 2. We're going to say 1 over 5 plus 1 over negative 2. And then we're going to flip that over to get F. Gives us a value of negative 3.33. Negative 3.33. If we have a negative focal point, go back here. A negative focal point means that it's a virtual focal point. And a virtual focal point is a diverging lens. Which is what the question was asking us. What type of lens do we have? A diverging lens, where rays of light diverge away from the focal point. Oh yeah, let's take a look at our last question, number 4. This is a 20 centimeter tall inverted real image. Okay, so we're going to say HI here is 20 centimeters. If the image is inverted, then HI is positive or negative? Negative. Good, Alex. Negative 20 centimeters. The image is formed 10 centimeters from the lens. So we're going to say DI is 10.0 centimeters. But we don't know whether we have a positive DI or a negative DI. Or do we? If it is a real image, we go back to real and virtual here. A real image would mean that we have to have a positive DI. F, DO, and DI go with real and virtual. A real image is a positive image distance. So we're going to make that positive. If you missed that when you were doing your homework from Tuesday, you'd get away with it. But we want to get it right because don't want to just get away with it. We want to do it right. The object is 8 centimeters tall. We'll say HO is 8.0. We'll make it positive because we'll assume the object is right side up. Actually, it tells us it's right side up. We want to determine, that should say the image distance. No, we want to find the object distance. We want to find the magnification, the focal length, the attributes, and the type of lens again. In other words, same stuff as we found before. DO, we want to find M, we want to find F, and we want to find the attributes and the type. Okay. And the last question, we tried 1 over F, that didn't work. So let's try right away this time M. M is equal to, we could say HI over HO, or negative DI over DO. Let's try the HI over HO. Negative 20 divided by 8, which is negative 2.50. We got a negative magnification. That should tell us that we have an image that is what? A negative magnification. Remember, M, HI, and HO signs go with upright or inverted. A negative magnification, CJ tells me what? It tells me that it's inverted. The image is going to be flipped over upside down, like the image on the retina of your eye is flipped over upside down, right? Take biology class. You know, the images that we see is, we see it as right side up, but that's our brain that makes it right side up. The actual image on our retina is upside down or inverted. Now we can find probably DO by saying AM is equal to negative DI, I should say, over DO. Solving for DO this time. DO goes up, M goes down. Negative DI over M. Does that make sense? Negative DI over the magnification of negative 2.50. That gives me positive 4. That means we have a real, well, we already know we had a real image, I guess, because we were told that we have a real image. But the positive DO tells us that we have a real object, which we would expect, because in physics 30, it's always real for it. It's never going to be a virtual object. It's always a positive DO. We got a negative DO, it means we made a mistake. We know this. Okay, we know this from Monday and from Tuesday. If we have a negative DO, it's always going to be, if we have a negative DO, it's going to be a mistake. Now let's do our lens equation. 1 over F is equal to 1 over DO plus 1 over DI. F is what we're looking for here. DO is 10. DI is, no, it isn't. DO is 4. DI is 10, both positive. So let's pull out the calculator on this one. 1 over 4 plus 1 over 10. Let's flip that over to get F, and we get a value of 2.86. It's positive, and a positive F means that we have a real focal point. And a real focal point means that we have a converging lens, where rays of light actually come together and converge at the focal point.